Hello friends, today we will discuss about the Sophomore's dream integral. This is the second video on the calculus mystery series. So let's see what's so special in this integral. In this integral we have to integrate from 0 to 1 x raised to the power minus x dx. So if we plot this function x raised to the power minus x in Desmos, then we see that this graph is obtained and this is the graph of x raised to the power minus x, and we have to find the area under the curve such that the area between 0 to 1, we have to find this shaded region, and integration is basically finding of areas, as we all know. So we have to find this area. So this is the given integral. We write it as e raised to the power natural logarithm of x raised to the power minus x dx. Now in natural logarithm we know that whatever is in the written as the power, this can be brought forward to the coefficient. So minus x brought forward to the coefficient of ln x. Now we will make some substitutions from the power series expansion. We know that e raised to the power x is equal to summation n equal to 0 to infinity x raised to the power n by n factorial. Replacing this x with minus x, we get e raised to the power minus x is equal to summation n equal to 0 to infinity minus x raised to the power n by n factorial. And in this minus x, suppose we replace this minus x with minus x ln x. So we will get e raised to the power minus x ln x is equal to summation n equal to 0 to infinity minus x ln x whole raised to the power n by n factorial. So this is the power series expansion of e raised to the power minus x ln x. Now this value can be put over here. So the integral can be seen as 0 to 1 integration summation n equal to 0 to infinity minus x ln x whole raised to the power n by n factorial, and integration is with respect to x. So this is a uniform convergence, that is the sum that will be obtained will be a convergent, and we can proceed with the further solution. So now what is happening, this summation and this n factorial are brought outside the scope of the integral operator, because this integral operator will not be operating on these terms. So we brought it outside the scope of integral operator, and the rest things are written as it is. So we will find the integration of this, only this. Now we have to find the integral of this from 0 to 1 x raised to the power n minus ln x raised to the power n dx. We will do some substitutions. First of all, we will consider this minus ln x as u, then minus u is equal to ln x, and e raised to the power minus u is equal to e raised to the power ln x. And we know that when e is raised to the power something like natural logarithm, then e and natural logarithm cancels out, and only the power part that remains was x. So it can be written as e raised to the power minus u is equal to x, and if you differentiate this, x becomes dx, and differentiation of e raised to the power minus u is minus of e raised to the power minus u, and the differentiation of u is du. So we write minus e raised to the power minus u du is equal to dx. So we got these many values, and these many values can be put in this integral, and we obtain this following integral. How? Instead of x raised to the power n, we are writing e raised to the power minus u n. In place of minus ln x, we are writing u raised to the power n, and in place of dx we are writing minus e raised to the power minus u du. All these are coming from these substitutions. The next is, we will change the limit, because here the limit is 0 to 1 when the integration was over x. Now the limit will be from infinity to 0, because the integration is over u. So how is this limit changing? When x is equal to 1, x equal to 1 we will put over here, we will get u is equal to minus ln 1, and we know that ln 1 is equal to 0, therefore u equal to 0. That is, when x equal to 1, u was equal to 0, so we write u equal to 0, that is the upper bound of the integration. Now when x is equal to 0, so we put x equal to 0 over here, we will get u is equal to minus ln 0, and we know that ln 0 tends towards negative infinity, therefore ln 0 is negative infinity, and since a minus sign was also there in the previous, therefore u is equal to minus of minus infinity, that is plus infinity. So wherever it was written x is equal to 0, we will write u is equal to plus infinity, and this, so after substitution we get this. Now the problem is, the integration is from infinity to 0. and we know that the limit of integration, the range of integration is from lower bound to upper bound, but here we are saying it is from upper bound to lower bound. So this is absurd. We will use this negative sign to change the limit of this integration, that is we will change the upper bound to lower bound and lower bound to upper bound, that is we will interchange it. So when we use this negative sign will go and the limit of integration will change, that is from infinity to 0. Now it becomes 0 to infinity and the entire integral is as it is, only the negative sign will be removed because we are changing the limit of integration. After this, what we are doing, this minus un and this n can be written together as e raised to the power minus u common n plus 1, and u raised to the power n du is as it is. Now we will use that same integral that we got in the previous result. From here we will make some substitutions, that is first of all we will consider u whole n plus 1 to be equal to v. So dv is equal to du n plus 1. Therefore dv by n plus 1 is equal to du. So this value of du can be put, instead of du we will write dv by n plus 1. This is dv and this is n plus 1. So what about this part? E raised to the power minus u n plus 1. This part can be written as, see, this minus u n plus 1, that is u n plus 1 was equal to v as assumed earlier. So it can be written as e raised to the power minus e raised to the power minus v, that is only written over here, e raised to the power minus v, and u raised to the power n. Since u is equal to v by n plus 1, from this we can derive this one. Therefore when u is raised to the power n, we will get v is also raised to the power n by n plus 1 whole raised to the power n. That is only written over here, instead of u raised to the power n, it is v raised to the power n by n plus 1 whole raised to the power n. And this n plus 1 was from the substitution of du, that is we substituted du as dv by n plus 1. So we got all this. Now this n terms are constant and can be brought outside the scope of integral operator. So it will be written as summation n equal to 0 to infinity 1 by n factorial n plus 1 raised to the power n plus 1. And what remains inside integral is 0 to infinity e raised to the power minus v raised to the power n dv. Now wait, these parts are constant and outside the scope of the integral, so we have written outside the scope of this integral. But this is a very well known formula in mathematics. This is the gamma function. This is the gamma of n plus 1. So we replace this entire integral as gamma of n plus 1. After replacing it, we know that gamma of n plus 1 is equal to n factorial. So we wrote n factorial over here. Now this n factorial and this n factorial will get cancelled, and we will see only 1 by n plus 1 raised to the power n plus 1. Now it is under summation n equal to 0 to infinity. Now suppose we change the limit of summation from n equal to 1 to infinity, that is we increase one term in the summation. So what is happening, we are getting summation n equal to 1 to infinity. Since we are increasing one term, so this n plus 1 will decrease by 1, because since the limits are increased by 1, therefore the value of n plus 1 will decrease by 1. So it becomes only n, that is n plus 1 minus 1, that is only n. So it is n raised to the power n, because we changed the limit from n equal to 0 to n equal to 1. So it becomes 1 by n raised to the power n. Now when n raised to the power 1 by n raised to the power n is brought to the numerator, we can see it is n raised to the power minus n. Now this is a very surprising result. You see, it was integration from 0 to 1 x raised to the power minus x dx, and we got the answer as summation n equal to 1 to infinity n raised to the power minus n. So it's quite surprising to see that the function that we integrated is the same function that we got after integration. Means the area under the curve x raised to the power minus x is the same as that of the function. So it's quite amazing, that is the integration, after doing the integration we are getting the same function. So this is one of the most amazing and mysterious part of this integral, discovered in 1697 by Johann Bernoulli. He was a French mathematician, and this was my effort to tell what is this Sophomore's dream integral, where the function is itself its own integral, that is integration from 0 to 1 x raised to the power minus x dx is equal to summation n equal to 1 to infinity n raised to the power minus n. So basically what is happening, integration is continuous summation and this sigma is discrete summation. Therefore, the continuous summation from 0 to 1 for this function is equal to the discrete summation from n equal to 1 to infinity for the same very function. So this is a very mysterious example where we can see that continuous function and discrete functions both are having the same answers and the same input, means the same function and the same answers are coming. I hope my presentation is clear to you. Thank you for listening. Thank you.